Interruptions, so to let everybody know, interruptions are allowed. And so just ask Marcus question if you need to. But before we get started, it's my pleasure to welcome Marcus Bruggen from the University of Hamburg. Marcus is an old friend. I met him probably, almost 20 years ago, back when he was doing different things. This was, well, I'll give you his background a little bit. He was an undergraduate at Cambridge, got his degree at 95, and he liked it so much there, he did his graduate studies in Cambridge, I think with Andy Fabian, if I remember correctly.
That was Douglas Goff, actually, on solar physics.
Is that right? Oh, okay.
I had a stint in solar physics, yeah.
Okay. Well, and then he went off and did a year's stint at MPI, and seemed to love Cambridge so much that he went back and was a junior fellow at Churchill College, although maybe they were sort of concurrent. Is that when you started working with Andy?
Yeah.
Okay, in early 2000s, and at that time, the feedback in galaxies was becoming started to explode as a field, and Marcus was one of the early theorists that worked out a lot of the physics of feedback in galaxy clusters, a lot of the hard stuff, including, how the energy is dissipated throughout atmospheres and the roles of conduction and other and cosmic rays, and heating atmospheres and keeping galaxies, from getting too rambunctious and forming too many stars. And that work is very well known. And then after that, based on that, he went off to Jacobs University, where he became a professor. And I didn't realize you were there for quite a while, 11 years at Jacobs. And then in 2012, he got a full professorship, a W3, at the University of Hamburg, where he's since built a very large group studying a number of things. But over that period of time, Marcus switched gears into acceleration mechanisms and looking at very large scale radio sources and galaxy clusters. And I think some of this was spurred, so he sort of maneuvered from being mostly a theorist to a theoretical observer, shall we say, or whatever, a mixture, a very nice mixture. And so now he's with the advent of LOFAR, which I think you're going to describe today. He's now moved in, and he's running a group that's really leading the effort to understand very large-scale radio sources and galaxy clusters driven by various mechanisms, and he's done a lot to push that field forward and to teach us about acceleration mechanisms and the dynamics of the outer parts of cluster atmospheres. So with that, I'll turn it over to Marcus for what I expect to be a very interesting talk. Marcus.
Thank you, Brian. Thank you, Brian. It's a pleasure. I already said in the beginning, before most of you joined, that it's a real shame. I've been talking with Brian for many years to come and visit, and I will hopefully do this once this whole spiel is over. And yeah, thanks for the too kind introduction. I still work a little bit on AGN, and I actually have some graduate students of Brian's in my group, and I'm still working on AGN feedback there. Actually, we're just preparing some papers. You may ask me about this later on, but now I'm going to talk about particle acceleration on vast cosmological scales, and I'll go and share my slides. We can all see them. So this is what I'm going to talk about, particle acceleration on cosmological scales, try to introduce you to a whole class of sources that are really quite mysterious and that not many astronomers really know about, but we've come a long way, and I'll give you some update, including quite a bit of work that's not even published yet. So if you look at the radio sky, the sky looks very different. This is, I think I got from the NRAO, a visualization of what the sky would look like if we had eyes that were sensitive in the radio. What you see now is not stars mostly. It's something that's called the non-thermal universe, really. So what you see is very fast electrons that emit synchrotron radiation in the presence of magnetic fields. So you see relativistic particles, electrons with Lorentz gamma factors that are quite large, hundreds of thousands. And you can see things like supernova remnants, that you see here, or radio galaxies, which are large clouds or jets of plasma that are ejected and accelerated by the environment of supermassive black holes. So it's very, very different. You get a very different view of the universe, and radio astronomy is not even 100 years old. And I'm going to tell you a little bit about some kind of sources that are in the sky. These sources sit in galaxy clusters. So if you imagine a galaxy cluster, you've all seen images of galaxy clusters before. This is an optical image of the galaxy cluster. You see here many, many galaxies here in this cluster. These consist of hundreds to thousands of galaxies. Often very massive elliptical galaxies live at the centers of these galaxy clusters. And Brian has led most of the work on what these massive galaxies do to the cluster at large. And this is what you see. You see these galaxies there, the light from all the stars and the galaxies. And the space in between all those galaxies that looks empty on this image is filled with gas, actually, with more gas, with more baryons than you can see in the stars here. And that light, or that gas, becomes visible in the X-rays, and the X-ray fills the space between all these galaxies. It's a very dilute, not very dense. We're talking about less than a particle per cube centimeter medium there that fills all this space. It's very hot. It's hotter than the center of the sun at millions of degrees, and it emits thermal Bremsstrahlung. And this has been known since the first X-ray observatories went up. And in the course of this talk, I'm going to talk eROSITA, which is one of the projects that I'm involved in, and that is just producing the first results. Now, this is the X-rays, from the optic to the X-rays. Now, if you go to the other side of the electromagnetic spectrum, if we look at this stuff in the radio image, here you see that same cluster looks, again, very different. What you see is, again, that space between the galaxies seems to be filled with radiation. This is here 21 centimeter radiation, if you like. This is continuum emission. This is emission that has a very broad spectral range. That's the nature of synchrotron emission. That's a very, very featureless emission that you see here. It fills large parts of this cluster volume, and you see other very strange sources here. At the bottom, you see a length scale, and you see that these sources are very large. Yeah. Now, very recently, we found one that's more than 3 megaparsecs long. These features. What are these? These features are pervaded by magnetic fields that are fairly strong, microgauss fields, yeah, in the middle of nowhere, essentially, in the cosmos and in the outskirts. They often have a steep spectra, and here's what these spectra of synchrotron emission look like as a function of frequency. You can see the flux here, the brightness you can imagine as a function of frequency. Here's gigahertz, here's 100 megahertz here, and these sources are quite steep. What this means is that the electrons have suffered losses, have lost energy, and the synchrotron emission works that the high energy electrons lose energy the fastest. So that's why they become steeper with age. These kind of sources are diffuse radio sources. These sources are typically classified as either radio halos. These are the large diffuse radio sources that fill the cluster volume, the size of megaparsecs, mostly unpolarized emission, and they are found not in every galaxy cluster. Unlike the X-ray emission, it's found essentially in every galaxy cluster, but they're mostly found in clusters that have undergone a merger, have been disturbed, and have crashed into other clusters, as clusters do as they grow to form even larger clusters. And then, on top of that, there are these sources that I described in the previous slide, and these are called radio relics. They sit at the outskirts of galaxy clusters, these lengthy filamentary sources, that the radio emission is polarized. Again, they're also found in disturbed clusters. These sources have been known for a little while, but not very many of them have been known until recently. And all these sources are produced by electrons that are very fast. And so how do you get electrons to be so fast? Or what you're looking at is essentially a cosmic particle accelerator. Now, going back to Enrico Fermi, he proposed mechanisms to accelerate particles. And he's got two mechanisms in which way you can do it. You can either scatter of moving clouds. That's fairly, if these clouds move at a velocity v, this acceleration rate goes like the velocity squared over the speed of light squared. It's very slow. That's a slow number, it's a small number. And because these clouds are both approach and recede, and it's just like a random walk, you can imagine that this is fairly inefficient. In shocks, there's something that's called shock acceleration. And that is first order, otherwise sometimes also called Fermi-1 acceleration. That's faster because it goes like v over c. And that's the kind of emission that's studied quite well in supernova remnants, where you see shock waves, quite strong shock waves, Mach numbers of hundreds in supernova remnants, that they produce and accelerate particles there. So these are two things that have been around for a long time, two mechanisms in there. So this is what you can imagine that Fermi-1 acceleration looks like, that you bounce particles back and forth the shock front, and every time they cross the shock front, they get an extra kick. You tap into the free energy of these converging flows in the shock waves, and then you form a parallel distribution of energies that go up to very high energies or high Lorentz factors, and these population of electrons then can emit synchronous emission. So what you need is a shock to produce this. Or if you have Fermi-2 acceleration, you need clouds, meaning scatterers of these electrons, moving around at some turbulent velocity. So that's sometimes also called turbulent acceleration. So if you've got a lot of turbulence, you can accelerate particles this way. So far, the very basic theory, this kind of textbook stuff that you can find and that's been looked at. So how does that relate to the problem that we have? So first, a little cautionary remark that the kind of shock waves that we're talking about on vast scales in the cosmos are not the kind of hydrodynamic shock waves that you can see, for example, in bullets or supersonic planes or the other kinds, but the shock wave is mediated by the molecular viscosity of the shock, but these are plasma shocks. These are essentially collisionless shocks where magnetic fields play a large role in doing it. So I'll ignore most of this, but you should bear that in the back of your mind that things may work differently in space than they do in the lab here. So how does that relate to galaxy clusters? Now, I mentioned that I'll focus on galaxy clusters that are merging because these are the types of clusters that display these phenomena. And here you see an image of two galaxy clusters are nearly the same size that go and run into each other here, almost head on. What you see here in magenta is the kind of gas that got stuck in the middle because it feels the other gas, so it gets stripped off as these two galaxy clusters cross each other. You see the galaxies here, and you see in blue the dark matter, which in this case is revealed through weak lensing. So here's the key down here. So you've got these three components, and how does then this unfold such a merger? Now let's go and have this simple cartoon. Let's take two galaxy clusters. The gas sits inside the dark matter. So I drawn this in purple. The galaxies sit on top of that as well. These, under their mutual gravitational acceleration, these two clusters go and attract each other and fall onto each other. And as they merge, the dark matter and the galaxies that are totally collisionless go and move on. The gas gets somewhat separated, and along the axis outside you get shock waves that form. And these are the shock waves that we think are responsible for the relics, for these huge structures that go and accelerate cosmic ray electrons, or very fast electrons, another name for very fast electrons. Here are some of the most famous examples. This is a relic I found together with Reinhard van Beeren when he was still a student using GMIT, and it's called the sausage relic. And it sits in this galaxy cluster. It's 2 megaparsecs long. You see in red the radio, and in the blue the X-ray emission from this cluster. So this is a cluster that's quite elongated here. So it has resulted from the crash of two clusters along this axis that I'm showing here with my mouse. And you can see here these relics, this diffuse emission. Now this is emission that doesn't come from a single source, like a single radio galaxy. It really comes from the shock wave. That's the hypothesis that we then tested. So here is zoom in into that same sausage relic here at the north of this galaxy cluster, to the GMIT observations. And you see here, this is where we see shock, where the leading edge of the shock wave is believed to be. And if the particles are accelerated, so this shock wave is moving outwards. If you remember the cartoon I showed you earlier, the shock wave is moving outwards, so the particles get accelerated at this white line that I drew onto here, and then they get ejected downstream, and then they should go and form this radio emission and slowly fade as the synchrotron losses from these electrons start to dig in and eat away at the electron distribution of these particles. Now, simple Fermi theory, DSA stands here for diffuse shock acceleration, another name for this Fermi type 1 acceleration, tells you how the spectral index of the radio emission, so the features of the spectrum of the radio spectrum, are related to the underlying Mach number here of the shock. You can go and test this. The shock waves that we are talking about here in galaxy clusters are weak shocks, because these are virialized systems and they collide with the same kind of almost virial speeds. So, and the sound speed is set by the depth of the gravitational potential. So Mach numbers are about 2 or 3 at most. Okay, so we're talking about weak shock waves. This is going to be important later. Now, these electrons get emitted, they move as the arrows indicate, and they lose their energy. And what you then see is that the spectrum here is on the top panel, you see the spectrum of it. So the brightness is a function of frequency. And over time, you should see that the spectrum gets steeper and steeper as these electrons suffer losses, because they shine in the radio that would make us see it. You can test this. And at the bottom is the measured spectral index map of this relic, and you see here that it does actually do exactly what you think. It's shallows here in the green at the leading edge, and then becomes steeper as you move away from the leading edge of the shock. So this is it seems to be true. Now you have to check whether it's actually a shock there, and this is very difficult. As Brian knows, as a seasoned X-ray astronomer, that getting this X-ray emission goes like the density squared, and the density in galaxy clusters drops down quite quickly if you move to the edges of these galaxy clusters. So it's very difficult to actually get photons there. But we checked it. We do see shock waves exactly the way you would see this, and these shock waves are seen as discontinuities in the brightness. Also, the radio emission is polarized. You see here, these are VLA emissions of that same source, the electric field vectors here, and they are all perpendicular to this arc. So that means the magnetic field is pretty much aligned on very large scales with the shock surface in here. Incidentally, when we looked back and looked at old notes by the late Gerda Brown, he found something of this source already in using the Wentz to the Westerbork telescope in the northern part of the Netherlands here. And you can see here, he didn't know what it was. He thought it was a head tail, perhaps it is not. So this is a very bright source in the sky. And this has been now looked at with many observations. This is, for example, a fairly recent JVLA paper here by Gabriele Di Gennaro. He works with Reinhardt in Leiden. You see quite a lot of structure here in these relics. This has been now probably the best studied relic so far. There's quite a few of them now, about 50, I guess, or probably a bit more of these systems that we have. Here's another spectacular one that we found. We call this the toothbrush relic. It's the handle of the toothbrush. It's the head of the toothbrush. Again, you see here now in green the radio emission, and in purple you see the X-ray emission from here. A vast structure. This one's even larger, and it's got actually more structure to it. As you can see here, very recent stuff by Kamlesh Purohit, who studied this. And there's now, with these deep and high resolution observation, you see quite a lot of stuff in there. You see that the toothbrush has bristles, as toothbrush should have, and got a ridge, and there's all more things that are going on here in the handle. And so yeah, there's more stuff that you can see. Again, if you look at the spectral index, you see that there is again this peculiar progression of the spectral index, which is shallowest here, and the spectrum ages as you move away from where we think the shock sits. Now, this is a complicated system. It looks a bit different from the other one. So we've done a lot of modeling on why it looks the way it looks like. I won't go into this because this is a source has already been described quite a lot. There's quite a few observations of some of these sources. Some of them look quite messy. This is another galaxy cluster. We see here that the relic looks like quite messy. There's also various radio galaxies that go and make things even worse here. And there's quite a bit out there. Now, let me tell you what I think the interesting physics is that is related to this. And these radio relics, we think that shock reacceleration happens at shocks caused by mergers of galaxy clusters. Now, if you relate the power in the radio emission to the total kinetic energy that is dissipated at the shock front, and that's half the area of the shock wave times the density, the upstream density, times the velocity of the shock cubed, and you take some efficiency eta of this, you can take a bunch of these systems here. It's work led by Andrea Bottillon and several others. You can plot the radio power here on the y-axis and the right-hand side here on the bottom side. You see they're a bit all over the place, and you can try and measure this eta here, and I'll come back to this later. Radio halo, you can do the same for radio halos. There you relate the synchrotron power to the total energy in the turbulence, because here turbulent reacceleration. That's in the whole volume of these disturbed clusters, you have a lot of turbulence, and you would think that this turbulence, through again the Fermi reacceleration, Fermi type 2 acceleration, you go and power these sources in here, and you multiply the energy of the turbulent energy times the volume in it, and again you have an efficiency eta, and you find these kind of efficiencies for radio halos. Now, you can test this again. So here is, maybe I go and you focus on here on the left-hand side. So these are plots for various relics where you plot these efficiencies. So what this means is what fraction of the shock energy goes into relativistic electrons. So what's the efficiency of my cosmological particle accelerator here? And this depends, there's an unknown, which is the magnetic field. It depends on the magnetic field somewhat here. And you see here for various magnetic fields, they are believed to be between 1 and 10 microhours, roughly speaking. And you can ask me later if you want to know why we think that is. And you can see here, these are the efficiencies of how much of the kinetic energies goes into the cosmic ray acceleration. And what you generally see is, these are quite large numbers. This is a percent. Of the order of 1% of the shock wave goes into these electrons. Here's a sausage one I showed you before, and there's various other famous clusters in here. And so this is a puzzle. Because according to theory, low Mach number shock waves should not be very efficient. And it's one thing to talk about shock waves that have got vast Mach numbers, but at low Mach numbers, it's very odd that they should be so efficient. So let me start with the problems. Why is the acceleration at these vast shock waves in the outskirts of galaxy clusters, why are they so efficient? And then of course, you also have to ask, where does the magnetic field come from? So what's the problem with shock acceleration? Like I said before, there's a lot of work on the theory side that says that low Mach number shock waves should not produce these bright arcs. Yeah, it will require an unrealistic fraction of the shock energy to be transferred into relativistic electrons. There's been various measurements, and there's a lot of theory on this as well. Maybe I skipped the second bullet, but another thing that I'm just going to mention in passing is that if a shock accelerates electrons, you would think that it also accelerates protons. Now, very fast protons, they would collide with the protons that are already there in the intercluster medium, and that would produce gamma rays through hadronic interactions. And people have looked actually quite hard using Fermi and other instruments to look for these gamma rays. There's no gamma rays there. So this tells you something about the shock waves. Namely, and we looked at this with my postdoc Franco Bazza, whose work I'll be showing throughout this talk, is that protons do not get accelerated very efficiently. It's just electrons that do this stuff. So how can this be? Well, one thing that you do have pretty much everywhere you look are radio galaxies that go and spew out into the cosmos vast quantities of relativistic electrons. And if you have already electrons that are there, and if you then run shock waves over them, then the whole process is much more efficient. And this goes by the name of reacceleration. Yeah, so it's similar to diffusive shock acceleration, but you already start with the seed fossil population in here. And then this is much more efficient. And there's a lot of people who worked on this. So this could help, provided that the whole upstream region of where the shock travels into, that this is fairly uniformly, some are populated with old electrons. Now electrons so if you look at the electrons, so these are relativistic electrons, if you look at the lost timescales of electrons, in gigayears, versus the energy of the kinetic electron energy, you can also plot this function of Lorentz factors or somewhere, you see that at very high energies, you lose very quickly energy. That's mainly synchrotron losses, And there's various curves depending on what the magnetic field is, because obviously if you change the magnetic field, you change the losses. And if you go to very low electron energies, so low relativistic energies, you also lose it quite quickly. The time scales are minute here. This is a log scale. But there's a place, a sweet spot somewhere in between here, where the electron loss time is actually the order of a Hubble time. So these electrons could sit around for a long time. And this is the idea of, or the hypothesis that perhaps this acceleration is so efficient because the cosmos is filled everywhere with these kind of electrons. And the rest of the talk, I'm going to talk about really whether this is actually true and how we can test this. Okay, so we can do some simulations, and Franco Bazza has put radio galaxies into big cosmological simulations and looked, where do they end up? Where do the electrons end up? The electrons are here now, marked in black, and you see here a radio galaxy in a large cosmological simulation that runs for several gigayears here. And you see in the background, you see the gas, and the black is really the electrons. This work that's just got the referee report for this shows you how do the electrons mix. There's a lot of interesting physics in there, something to do with the Schmidt number and about the interplay between diffusivity and turbulent mixing and anyways in there. So the bottom line is we don't actually really quite know whether it works, but it's feasible, and people are starting to look into the way in which the whole space in the universe could be polluted by these seed electrons that originate in radio galaxies. So
sorry, can I ask you again, what was the energy of these electrons? The peak that you had for the lifetime.
That's here. So this is the electrons in GeV. It's about 0.1 GeV.
Okay.
Electrons. So
Right.
gammas of like 100 or something.
So don't you expect like the thermal SC or some relativistic version of thermal Sunyaev-Zulovich effect from these guys?
But not, yeah. You would see this for the higher energies, you would see this in radio galaxies where the density is very high. Yeah, you would see this. And people looked for, of course, thermal SDs in terms of radio galaxies. But for the kind of densities that we are looking at, it would be, I don't think one would be able to see it.
Okay. Okay. Because I mean, I guess that I was thinking that could be a prediction you could test, but you're saying that's not, it's not a big signal.
That's not a big signal. I don't know if I have the numbers now at the top of my head, but we did look into this at some point.
Okay. Cool. I mean, the other thing it's interesting is, I mean, these, because they are kind of semi-relativistic, they would have a specific spectra that could be make them easier to distinguish. But yeah, I mean, it depends on signal noise. But yeah, I mean, we are measuring these much better than we used to.
That's true. So maybe there are clever ways with spectral templates or something to look for this.
Yeah.
So yeah, perhaps that's worth revisiting. Yeah.
Thanks.
And with the advent of the whole new generation of radio telescopes, people looking at radio telescopes, and this is NearCat data, this is actually unpublished stuff from very early NearCat stuff in the air. And one of the things that's beautiful about the results that come out of NearCat is if you see radio galaxies and you see this amazing structure, fine structure you see here, the source that Larry Rudnick's been working on. And so there's all kinds of things that go off, filaments, go off these radio galaxies. They obviously transport electrons outwards. So we're seeing a lot more detail. And I think what I'm trying to say is we're just at the beginning of trying to see how, what the fate of electrons are that originate from the environment of a supermassive black hole but end up all over the place. There's quite a lot of stuff in there, and there's a lot of work and a lot of physics I'm going to learn from this. I won't go into this. There's also a lot of work done again by Franco Batzer and people around him that look at how magnetic fields, because what you saw there is these structures are most likely driven by magnetic fields. That's, for example, also shown you by the polarization maps and others, but to look at the large-scale dynamo or the large-scale distribution of magnetic fields. This is again another topic. I won't get actually too much into magnetic fields here. That would warrant an entirely different talk. But measuring magnetic fields on this vast scale is very difficult. People do this with rotation measure synthesis and with various kinds of models. This is a model. This is an MHD simulation, cosmological MHD simulation here with very high Reynolds numbers. I think it's the biggest to date, at least it was 2 years ago. This shows, they showed then for the very first time that turbulent motions in this gas can quite efficiently actually amplify magnetic fields. And the topology of these magnetic fields will have to come into models of the large-scale distribution of cosmic ray electrons as well. So as Brian advertised in the beginning, I'm going to talk a little bit about LOFAR. This is, for those who don't know, LOFAR is a radio telescope and a radio interferometer that has got its center in the Netherlands. You see here, this is the so-called SuperTurf, which shows you that the Dutch are very gifted gardeners. They've made this whole artificial island, and what you see on here are two types of antenna. They're these black ones, they look a bit like solar panels, but they're just styrofoam boxes filled with dipoles. There's little containers full of electronics, and there's even simpler chicken wire antennas here. This is only the center. The whole telescope has got 52 stations that are spread all throughout Europe. We've got one here in Hamburg that we built a few years ago. And there's 6 altogether in Germany. There's one in the UK, there's one in Sweden, one in France, there's 3 in Poland now, and so on and so forth. And this is a radio interferometer that operates at frequencies between 30 and 240 megahertz, so very low radio frequencies. That makes it important to have long baselines to get decent angular resolution. And you can ask me later more about it. I'm going to show you some results of this. So this is an interferometer that has a very large field of view, which is very important to capture these extended objects in the sky. And it operates at megahertz frequencies. And that's important if you look at steep sources that become brighter if you go to lower frequencies. So that's why this is pretty much the ideal telescope. And you see the whole outline of the network as it is now. There's also the most recent stations in Latvia in here. You see here. So this has been in operation for I think 10 years now, and is going to get upgraded now to LOFA 2.0. Again, I can talk about this a little bit later. This is a little bit of a sales plot for this telescope. This shows you where its main benefits lie. So you see here is a function of frequency. You see here the sensitivity, and the lower the sensitivity, the better. This part is explored, and you see here various famous surveys. First, an NVHS done with the WCA, and you see the Westerbork one, and the one with the MWA in Australia now. And the survey that we've done, we are working on most is called the LOT survey at 140 megahertz here, and the LOL survey about 50 megahertz here, using the 2 types of antenna respectively that I've shown you in the picture before. So it really breaks into new parameter space here. The sizes here of these circles show you the resolution. So it's also because we've got these baselines of 1,000 miles, roughly speaking, you get a lot of, you've got a good resolution here, good angular resolution of, about 10 arc seconds at 50 megahertz, and much less, of course, it's at 140 megahertz. So this is quite exciting, and I'm going to show you some new results from this. I'm not going to recap LOFA results going back this years. I'm going to show you some LOFA results that we just got essentially in the last couple of years, and these are results that come from dedicated observations that go very deep. And next week there's going to be a paper splash that comes out from the LOFA collaboration that showcases a bunch of papers from these deep observations. And the most exciting one about my topic is, where do all the electrons and magnetic fields in the cosmos, how are they distributed on these large scales? And these observations, this is a galaxy cluster that's really well studied at L2255, and it's one of the very deep fields. What deep fields means is it's been exposed for 75 hours with a resolution that is afforded at these frequencies of about 5 arc second resolution here. And much of these structures are known. This is known to be a bit of a messy cluster, a bit of a train wreck of a merger. But if you look at this exposure, at this really deep exposure, you see stuff that goes out really, really far. And there's really this haze around this cluster that goes all over the place. Yeah. There could be shock waves here, but it's not quite clear where all this stuff comes from. But I think what I want you to take away from this talk is, if you go deep, and especially if you look at low frequencies, you see that the whole space around the cluster seems to be filled with relativistic electrons. So if you go for scale, if you plot the virial radius here, there's some indication that there's even emission beyond the virial radius, but everything inside the virial radius, there's significant radio emission above 3 sigma over the noise of diffuse radio emission. And on top of all the radio galaxies that sit here and the stuff that was known before, which is this stuff essentially. So that's interesting, and Andrea Bottillon is working on this. That brings me to this whole new idea of that we have that on top of the sources that I described in the beginning, radio relics and radio halos, there's a new type of source that we called mega halos. This is work that was done by an Alexander von Humboldt fellow that we have here, Virginia Cuciti, who has been working on these. And these are data that she looked at. So this is another galaxy cluster. It's the virial radius in here. And you see that almost the entire virial radius of the galaxy cluster is filled with a very low surface brightness diffuse emission. This is new. If you look at this same galaxy cluster here, and this cluster was known to have a halo, a radio halo, which is this blue stuff here, the points that are that's not really a fit, as we kind of fit by this line of the radio halo. What's new is all this stuff down here, yeah, that is indicated here by this magenta line. So emission that goes really out to the virial radius. So underlying diffuse emission, where you do see synchrotron emission. So that must mean there must be a relatively acidic electrons out there, and they are all quite steep. There's all quite steep emission. You really see this. It's difficult to get the spectra of this, but it must be steep because we really see it only at the very lowest frequencies, and it goes on for quite a while. And yeah, there's another cluster, one of these mega halos. There's all work that's not published, so please do not share this. And yeah, this is another one. So you see here the XMM contours, the XMM, not the contours here. So the white is what was known before, LOFA, HBA observation. This is the radio halo, normal, kind of not too exciting radio halo at the center of these galaxy clusters. Yeah, still quite large. No, it's almost a megaparsec across here. It sits inside the thermal gas that you see here in blue. This is the X-ray emission in here. But what the LOFA sees, if you carefully subtract this, if you really work hard on the data, what it brings out is this whole stuff, much larger than was known before. And this is the stuff that you see here in these data points here at the bottom. So this is not just stuff going out further. I think this is really a different kind of effect that you see here. And this still needs to be followed up and analyzed, but this is exciting new stuff that plays into this hypothesis at the beginning that probably the electrons are almost all over the place. So I don't have many answers. I've got a few questions. We don't know how common these are. They are very difficult to find. You need deep exposures, you need to go to low frequencies, and future facilities, especially the LOFA upgrade, are going to help here. What's a little bit striking, and I can go back a little bit, is what we find in these clusters is actually not shown here on this image, is that they actually contain quite a few striking and strong radio galaxies that somehow fly through the cluster. So perhaps this is an effect that only comes about when you do have very active radio loud AGN that a certain number of them or a certain power of them. So there could be some relation between the activity of radio loud AGN and the occurrence of these mega halos. Don't know what the relation is. Are they really powered by different physical phenomena? Or we don't know how these diffuse out. So I don't have many answers, but these are the questions that we're going to look at. So that's it for mega halos. Let me talk about another thing that's exciting, and that's in the same vein, if you like, and those are bridges. Now, what are bridges? Now, if you take two galaxy clusters here and imagine that they merge, galaxy clusters, the cosmos and the cosmic web, are all interconnected by these cosmological filaments, also filaments of gas. It's generally thought that the warm hot intergalactic medium sits inside these filaments. It's very difficult to observe these filaments. They are known because of the galaxy overdensities here, but not much is known about the gas in which they sit in. Whether it's accretion shocks that line these bridges is not clear. It's not clear whether there's magnetic fields inside of them, and it's not quite clear what state of the gas is. Is the gas turbulent, or is it laminar, or what does it do generally? So one thing to do is take a deep exposure with a radio telescope. Before you do that, you can do some simulations, and these are simulations of this non-thermal cosmic web. What you see here is are essentially magnetic fields in here. And you see here that these filaments, this Swiss cheese kind of structure that you see here, that these filaments are also lined with magnetic fields. So that's one thing that you need to make a radio emission. So do you see a radio emission? You can look at this, and here are predictions. In the X-rays, you get two clusters that are not too far away. You would imagine that they're synchrotron emission. This is work that we've done using simulations, cosmological simulations, and we looked for it. Well, maybe before I said we looked for it, maybe a few specs. These bridges, according to the simulation, they should contain enough power also in turbulence. It's about 10 to the 45 ergs per second here, as we have in turbulent power, and you only have to convert a little bit into radio synchrotron emission to see it. There's also some interesting predictions from these simulations that the turbulence is superalfenic, so the Alfvén Mach number is about 10. It's also solenoidal, meaning not compressive turbulence. The solenoidal turbulence has a particular kind of acceleration mechanism that's in there that predicts that at low frequencies you should get very smooth radio emission, and at high frequency you should get very clumpy radio emission. For a while, and so we can check this. And the first to check this was Federica Govoni, who published this in Science already almost 2 years ago, and found this pair of galaxy clusters, or that's been known to be a pair of galaxy clusters, Abell 401 and 399. It's been known from Planck to have gas in between. That's apparent in the SZ maps in here. And using LOFA, she found that these two clusters are also connected by a synchrotron bridge. So yeah, so it's quite not easy to say whether this is weak shocks or volume filling turbulence that produces this. So it's not clear where this comes from. We don't have a spectrum. Only LOFA can see this. So it's probably steep, but we don't know exactly how steep this is. Since then, people have looked at some other things. My previous postdoc, Annalisa Bonafede, looked at the Coma cluster, which was the first, incidentally, the first radio halo ever seen in here. The nearby Coma cluster, and here there's a relic also in the Coma cluster, and she looked at this bridge region, and again she found 140 megahertz here. She found emission, something that she called streams here, that go and seem to connect this group. There's a group here of galaxies led by this galaxy that has flown through this Coma cluster, and it does seem to produce diffuse emission there and here. There's enough turbulent power in it, and you can do a little bit of math. I'll probably shortcut this here because I'm slowly running out of time. You can constrain the acceleration efficiency in the Mach numbers from these kind of observations. Then there is another bridge that was found in about 1758 in here, and there's also some X-ray emission in this bridge region. It's fairly close. These clusters are fairly close. You can see here the 1 megaparsec scale bar in here. And what we found there was that if you overplot, you split the bridge region up into boxes and you plot the X-ray and the radio emission for all these boxes, you see that they are pretty much in sync, meaning where the radio emission is high, also the X-ray emission is high, or maybe the other way around. So this suggests that the synchrotron emission is volume filling. It's not just, imagine like you have a sheath going around this bridge region that only produces the synchrotron emission and not the rest. Then you would not expect this behavior. So it seems that volume filling turbulence in these bridges produces the synchrotron emission. Okay, so much for the, well, I'm going to say a bit more about the bridges, but I'm going to change wavelength again. I want to advertise a little bit this project that I'm involved in since about a year ago. This is called eROSITA, and this is an X-ray instrument on board as a Spectrum RG mission. This is a Russian mission, and there's a German-built X-ray telescope that sits on it in a hard X-ray telescope. So it's Russian-built, and that was launched in 2019 in September and flew to the L2 Lagrange point, and it has for the next 4 years the task to survey the entire sky. If you take off the covers, this is what eROSITA looks like. It consists of 7 of these Volta-type telescopes here. You see the baffles here in front. This is what an X-ray telescope looks like. The cameras, of course, are on the other side. There are a lot of concentric shells, 50-odd concentric shells that sit in here to focus the X-ray light. And this is the first map that was published just a few months ago here of the EU Zeta sky. It has completed its very first sweep of the X-ray sky here. It has already done some remarkable discoveries. For example, the EU Zeta bubbles that are larger than the Fermi bubbles. And so you see a lot of stuff here. You see a lot of clusters and supernova remnants and super bubbles and things like that, super clusters in here. And to preempt questions, this is, even though it's a proprietary mission, there is some things that are going to get released. There's an early data release that's we are planning at the moment. Next year, well, in July, it's going to come out. We've just finishing the papers here on various fields, and there's various all-sky surveys, 8 altogether. Every single one takes 6 months, so 4 years to complete the entire sky 8 times, and 3 instances data is going to get released in here. So we took the time for the calibration of the instrument to look at one particular bridge between these 2 galaxy clusters. Again, here's the galaxy cluster. This is actually a double cluster down here at the bottom. And we found diffuse X-ray gas in this bridge region. So just moving out of clusters and into these bridges is interesting. And we can measure temperatures there. And there's a lot of physics in there. But I was, of course, for the sake of this talk, mostly interested in the radio emission. That was too fast. And we looked at this. So one curiosity of this mission is that the Russians and the Germans decided, which is not a very clever thing to do, but they did this anyway, they decided to split the sky in half. So this, mostly the southern sky, it belongs to the German consortium and the northern sky to the Russian consortium. So we have, this is the cluster in the southern sky. So we use ASCAP, early science observation of ASCAP, which is an SKA precursor in Australia, a phased array feed dish array that you can see. And we looked at this here. You see here the X-ray image again. We tried to look for synchrotron emission in this bridge, and we couldn't find any. This is at 1 gigahertz. So that's odd. So it does seem to be quite steep, or maybe it doesn't come up all over the place. I'll probably skip this here. There's more stuff coming out of all these types of sources with the new generation of X-ray telescopes. And here, this is some unpublished work with MeerKAT and as well. And the superclusters that we found. And these superclusters also show radio and synchrotron emission on a number of fields. This is stuff that's mostly finished. I think it's time to wrap up, to try to summarize the story I've been trying to tell you, is that with radio telescopes, especially at these low frequencies, and especially the survey type telescopes with large fields of view, have shown that electron accelerations happens on vast scales, megaparsec scales. And while it was thought to be very rare, it's probably not that rare. It's just difficult to find. The electrons get accelerated by shocks and turbulence, but they probably need the pre-existing population. They need probably electrons to begin with that they can accelerate in order to explain the observations. So going very deep with LOFA, just in a matter of months, really, we found that there is a new type of source, they're called these mega halos. They tell us something about where these electrons come from, the provenance of these electrons, the way they might be produced in the first place, and also, of course, large-scale magnetic fields. I haven't focused much on these, but there's a few people in my group who really focus on these magnetic fields that you can see out there. So these seeds for particle acceleration could come from radio galaxies, and new observations of radio galaxies are really quite exciting to show you a lot of interesting phenomena that happens when these radio galaxies fizzle out at the edges. And you can learn a lot about plasma physics from there. Then you can look at bridges, I call them cosmological bridges, maybe that's cluster bridges, maybe a better term, where it seems that electrons get re-accelerated by solenoidal turbulence. And this is stuff that really comes out of simulations, analytical work, and radio observations. And I think we're just starting to scrape the surface of this type of radio sky, this part of the radio sky that has started with galaxy clusters, but goes beyond this now. And SKA and other telescopes will map the extragalactic distribution of both magnetic fields and cosmic rays. Okay, well, thank you. I think I stop here, and I'm happy to take your questions.
I guess we'll get virtual claps as well. Thanks very much, Marcus. Questions?
I had one question. So you've shown us, thanks, that was a great talk, and in particular, yeah, for those of us who didn't know so much about these different sources, I mean, it was a very good explanation of the steep spectrum sources, which always confused me. So you were showing us mainly resolved images. I'm wondering if these things were further away, can you get sort of integrated low frequency luminosities for a large number of galaxy clusters at larger distances? Is that a possibility?
Yeah, this is difficult to do. So people have looked into this, into stacking, whether you stack large samples of galaxy clusters, right? Whether you can go up there. This is very difficult. It's mainly difficult because of the damn radio galaxies in there. If you stack them up, and if you even got fading radio galaxies in there, you stack very many of them, it's difficult to disentangle the effects. There's some brave attempts. I think a student of Larry Rudnick, I think he's called is he called Shay? I don't know. He tried this, and he tried this and put on some limits. We're trying this also in these deep observations where and this is work by Eric Ozinger in Reinhard van Beren's group. He stacked them and done upper limits of this. So so this is a great idea, and people are doing it. It's just, I think the systematics is difficult, like it always is in stacking, but I think particularly in the radio sky, it's difficult. Especially since the beam is different for every single one, for every galaxy cluster. If you stack them, you've got to be very careful you don't get other things, putting in spurious signals from beyond. So it's very difficult. I mean, I've thought about this quite a lot, and I've actually shied away from this a little bit.
Oh, great, thanks.
Other questions?
I had a question. There was like a slide kind of early on that had like the contours with the spectral index for the sausage, I think, and there were some other things. Yeah,
there's this, for example, but
I was wondering about like the dot, like small source in the bottom left. Is there like a mechanism for that gradient where like the bottom right?
Yeah. Not entirely sure. This is a radio galaxy in here. Why it has that gradient, I don't know. Yeah, it's a good question. Don't know what the explanation for this could be.
Well, it looks like it's getting steeper as you move further away, right?
Yeah.
So maybe it's just.
So it seems to be the core. So this is close to the resolution limit of this map. You see, this is probably the beam size here, roughly speaking. These dots are roughly what the beam size is. Yeah, it should be. Good radio map should note it, but it's not on this one here. But you see, this is close to the beams. There's only probably a few beams across. So if there's a radio galaxy that injects fresh plasma here, and the jet goes this way, you would think it would steepen this way, and it's probably just badly resolved.
Right. Any other questions? So I'll jump in. I was really impressed with the image of the faint radio flux going out to R200, and it seemed beyond, and it made me wonder if a lot of this stuff, you see these galaxies flying through, if this is just stuff coming in along filaments flying in.
Yeah.
Right? So where would be the accretion shock on this? That would be sort of beyond.
Yeah, that's quite
that's a bit further out, right?
Yeah,
this stuff would have been processed through the, I mean, obviously it's a messy thing, as simulations have shown, but stuff would have been processed through the accretion shock.
Yeah, it's good that you mentioned this. So where could this haze come from? The haze could. So first of all, the haze is a bit messy. I see there's more here, there's less here. So again, we'll have to go deeper. Although it's not much deeper you can actually go because of confusion limitations and things. But we can try and go a bit deeper and see where this comes from. Does it come from the accretion shock, which is quite a bit out of this range? So where matter falls into the potential well and gets shocked. These Mach numbers, the shocks and these accretion shocks are quite high Mach numbers, so they could potentially add to the electrons. They could do, yeah, but the densities are quite low, so it's not entirely clear how much their contribution would be, and whether you would, one way to test this to see whether you've got large, where does the stuff fall into this cluster, from which directions, and do you see the haze preferentially in the direction of where stuff falls into, and that could be.
Yeah, if you put a galaxy map on it, you could just do galaxy density contours and look to see if there's some relationship there.
Yeah. So my hunch is that more important than these accretion shocks are actually radio galaxies themselves. This could be wrong, but if you look at radio galaxies, you do see stuff that comes off it and almost fades into other stuff.
Yeah.
Now, radio galaxies, of course, only have certain duty cycles and they fly around. It's difficult to trace it back. There's some studies of spectral index map, and there's a person of mine, Francesco De Gasperi, and he looked at some of these sources, these radio galaxies, and found that this plasma goes off it and it fades into the haze, and then the spectral index goes back up again, as if those little electrons that are being spewed out by these radio galaxies, they go and get join the cluster weather, as it's sometimes called, and then get kept at some sort of energy level that then persists inside the cluster. So I think that it is more related to radio galaxies. So if we find more of those, maybe we can look at not just the spatial distribution, but also the relation to the radio galaxies, or like I said, overlaying galaxy maps or radio galaxy maps to see whether what's in. So my hunch is actually radio galaxies produce this. Yeah,
and they could be coming in.
They could be coming in. That's right. It could be both. Yeah.
So any other questions? Just jump in.
So yes, I can also say a little bit about Rosita. That's now doing, finding a lot of clusters.
The Rosita data is phenomenal. The other thing is it's so, you should be able to put limits on turbulence speeds just using the coherence of these trails, because they're remarkable. They go on for megaparsecs.
Yeah, so this is one thing that's very weird, and this is the stuff that I've been looking at Tom Jones and Larry Rudnick, looking for these things. So why are these things so straight?
It's just weird.
It's really weird. So these are 200 kiloparsecs, I think, something like this. Here you see a spectral index map up here in the top, and the electrons, and we see this in a number of cases. The electrons start to age a little bit, but they seem to live for longer than you would think, and they sort of stream along these flux tubes in here. It somehow sometimes it reminds me of this picture of the galactic center here. Let me see. I think let me unhide the slide. You've all seen this image from the Meerkat collaboration of the galactic center. This is the center of the Milky Way, 1 gigahertz. And you also see all these things here. These streamers, sometimes are called harps because they got several filaments, these flux tubes out there. This is also synchrotron emission from these sources. So yes, so my only explanation is for the nature of these sources, they must be magnetically dominated. And the polarization map also suggests this. It's like almost like little funnels into the ambient space where you channel all these electrons.
Mm-hmm. So long tubes.
Long tubes.
Essentially isolating the emission. Yeah.
Long tubes. And so a lot of difficult physics about how to make these tubes. We don't even know how the lobes of the radio galaxies, what kind of magnetic structures they really are. And
Yeah, that's amazing. Any other questions?
What are the magnetic fields in the filament of the magnetic fields in those extended structures?
So was that a question or was that background?
No, that's a question.
Sorry, can you say it again? I couldn't hear it.
Hello.
Uh-huh.
What is the strength of magnetic fields in those filaments that you just showed, like those extended from the halo of the radio galaxy that just go away?
What the magnitude was so we don't know. What you can do is you can do models of where you look at the spectral distribution along here and you assume what kind of velocity might they be streaming with. If you set this, say, to the Alfvén speed,
Okay.
a bit arbitrary actually, but you could set it to the Alfvén speed and then go and look at how does the spectrum age in here, and then that would give you a magnetic field. But it's probably all wrong what you get out, because for one, they might not stream at the Alfvén speed. Plus, what's obviously happening is they're not just sitting there and aging. What you can see here, where these yellow lines are, this is a region where there does seem to be a bit of turbulence here, and there the spectrum actually becomes again flatter. So again, these electrons, they interact, even though they are probably confined to this flux tube, they interact with the cluster weather or whatever there is in there, and they go and gain energy. All these processes are very poorly understood. So then you can make estimates about the stability of these flux tubes and say what kind of magnetic fields would you need for these flux tubes. So it's difficult. You end up with some microgauss fields of some sort, but it's very difficult to be any more precise.
Okay, thank you.
So we're pretty much out of time, but we can entertain one more question if you have it. Otherwise, I don't want to hold up Marcus too long. It's a little toward evening there, I guess.
It's almost 7. It's almost 7. Quarter to 7. Yeah, it's not fine. It's fine. It's not as bad as I was attending a workshop at the KITP over last month, that specific time. So that was long evenings.
Okay, well, yeah, thanks very much, Mario. That was really a marvelous talk, and the data just keeps getting more and more